Hello everybody. The topic of today's presentation is the Bohr model. So far in our exploration of the evolution of the atomic model, we have covered three models: Dalton's, Thomson's plum pudding model, and Rutherford's nuclear model. Let's revisit Rutherford's model. While Rutherford had a great deal of experimental evidence showing that the atom is mostly empty space with a small, central, solid, positively charged nucleus, his model was less successful when it comes to the electron. In fact, just as a satellite orbiting the Earth eventually loses speed and comes crashing down, so would an electron be drawn into the nucleus, thus obliterating the atom itself. Since that doesn't happen, that's a bit of a problem. Additionally, Rutherford's model could not explain bright line spectra. In fact, if his model with respect to electrons were correct, emission spectra could not exist at all. So again, big problem. How to explain this? Energy levels. Bohr proposed that an electron moves around the nucleus only in certain allowed circular orbits. Suppose the stairs represent energy levels in an atom, and the kitty represents an electron in its normal position. We call that the kitty's ground state. The kitty may move up or down the staircase, but she must do so in whole numbers of steps. She can't be anywhere in between. She can't be at step 2.33. As the kitty moves upward, her potential energy increases, but only certain energy values are possible, nothing in between. When the kitty moves upward, she absorbs only certain packets of energy. This is an excited state. As the kitty moves back down, she releases only certain packets of energy, the same packets of energy, in fact. So, when she returns to her normal position, she is back in ground state. Each electron orbit in Bohr's model has a certain energy value. The fixed energies an electron can have are therefore called energy levels and are symbolized by a lowercase n. The further an electron lies from the nucleus, the more energy it has. Thus, a quantum of energy is the amount of energy required to move an electron from one energy level to another. Like the kitty, when an electron jumps outward one or more energy levels, it absorbs certain quanta, or photons, of energy. When an electron drops back inward one or more energy levels, it emits certain quanta, or photons, of energy. When a photon is absorbed, the electron is excited. This is naturally an unstable condition. So when the electron releases the same amount of energy, the same photon it absorbed, it returns to ground state. We can now use Bohr's model to explain emission spectra. Like the rungs of this weirdo ladder, the energy levels in an atom are not equally spaced. The higher the energy level occupied by an electron, the less energy it takes to move from that energy level to the next higher energy level. It's as if each stair in the kitty's staircase became shorter the higher up the staircase she goes. Therefore, the kitty doesn't need as much energy to move from one stair to the next. The photons of energy she absorbs and releases become smaller and smaller. As you have seen in lab, when hydrogen atoms are excited by heat or electricity, a bright line spectrum is visible through a prism, that is, a spectroscope. Recall that hydrogen's bright line spectrum has 4 visible lines. According to Bohr, each line in the bright line spectrum of hydrogen corresponds to one type of drop inward, that is, one energy of photons being emitted. Here's a simple animation of how this works. We are looking at the hydrogen atom along with 5 energy levels. First, let's excite the electron. The electron absorbs energy to move from n equals 1 to n equals 3. When it drops from 3 to 2, it emits energy. Note that when the electron drops from energy level 3 to 2, a red photon is emitted. Now, let's excite the electron again. The electron absorbs much more energy, moving from n equals 2 to 5. When the electron drops from 5 to 2, it must therefore emit a higher energy photon. The color of this higher energy emission is blue. So, as the electron's drop inward becomes larger, the energy of the photon emitted becomes higher. The transition from n equals 3 to 2 releases a red photon, 4 to 2 green, 5 to 2 blue, and 6 to 2 violet. Red, green, blue, violet. Bohr then predicted the existence of lines in other regions of hydrogen spectrum. He predicted that drops from higher energy levels to n equals 3, for example, would emit infrared photons, and that drops from higher energy levels to n equals 1 would emit ultraviolet photons. Of course, he had no way to prove that at the time. However, when technology became available to detect these lines in hydrogen spectrum, they were exactly where Bohr predicted they should be. So, Bohr's model is looking pretty good, right? He explains bright line spectra. He accurately predicts IR and UV lines in hydrogen spectrum. I mean, after all, a good model not only explains the data you know about, but accurately predicts the data you don't. On the plus side, we now have an explanation for hydrogen's complete emission spectrum. However, Bohr's orbiting electrons are still going to crash into the nucleus. Oh, and his calculations only work for hydrogen. Speaking of hydrogen, please exit the screencast and watch the video on the next slide. It reviews Bohr's model of the hydrogen atom. Thanks for watching.